Welcome. Today we'll work through several exercises that will help us review some probability topics. But before we get started with the problems, let's just briefly review the idea of a probability model. So if we have a random experiment, there's going to be some number of outcomes that that experiment can have. And mathematically, we'll describe that experiment as the set of outcomes, which is customarily denoted capital omega, together with a function little m that says how likely each of those outcomes is. This pair omega comma m is called a probability space. The point of coming up with a probability model is to be able to translate questions about real-world random experiments into questions about the mathematical object and vice versa. That will allow us to formulate rigorous, precise statements that correspond to various quantities of interest in the context of the real-world experiment. So for example, if you flip two coins, the possible outcomes are heads, 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 tails, tails, heads, and tails, tails. So that's our probability space. And for a fair coin, those four outcomes will be equally likely. So our probability mass function is constant. And the question is, what object corresponds to first flip comes up heads? That's something that we understand what it means in the real world scenario, and we want to have a mathematical object that corresponds to that. And looking at the probability space, we can see that the first flip comes up heads is a statement which is true about these two outcomes, and it's not true about these two outcomes. And a function which is either 1, in other words true, or 0, in other words false, on each element of the set omega is a subset of omega. So that leads to the idea that events are subsets of omega. The second problem asks us how to find the probability of an event given a particular probability space, omega comma m. And the idea is going to be that we just sum the probability mass of each outcome in that event. So if our event consists of these two outcomes, then the probability associated with that event is going to be the sum of the masses of the outcomes in that event. So in this problem, we're developing more correspondences between descriptions of events that we might use to describe a real-world scenario, like two events both occur, or an event does not occur, or one or another event occurs. And we're writing set theoretic operations to describe these things. So E and F both occur means that the outcome which actually occurred is in the set E and in the set F. And that is the intersection operation. The event that E did not occur is the event that the outcome which did occur falls outside the event E. In set theory language, we would write this as omega without E, or E complement. Finally, the event that E occurs or F occurs is the event that the outcome that actually occurs is either in E or in F. And in set theory language, we call that the union. So if n friends enter the lottery and we denote by E sub I the event that the ith friend wins, So this is for each I from 1 to n. Then the event that at least one friend loses is the complement of the event that all the friends win. So the event that all the friends win is the intersection of all the E events. And then we're taking the complement of that here. The event that all the friends win is just the intersection of the events. And the event that at least one friend wins is the union. So this problem asks us to think a little bit more about the distinction between the probability measure P and the probability mass function M. So if omega has 4 elements in it, then the probability mass function has a domain which has 4 elements in it, since its domain is omega. However, the probability measure has a larger domain because there are more events than there are outcomes. For example, there are these 4 singleton events. There are also events which contain 2 outcomes. There are events which contain 3 outcomes, events which contain no outcomes, and one event which contains all the outcomes. So there are many possibilities. And the easiest way to count the number of subsets of omega is to think about formulating a subset as a process of choosing one at a time for each element, whether it should be in or out of our subset. So we get one choice here with 2 options. And then we get another choice independent of that one. Again, 2 options. Altogether, we have 4 choices, and in each case, we have 2 options. So the cardinality of the domain of P is 2 times 2 times 2 times 2, which is 16. Suppose we define 2 events A and B, one that the Red Sox win by 5 or more runs, and the other that the Red Sox win. The question is, which of the following is necessarily true of those 2 events regarded as set theoretic objects in our probability model? So this first one says that A and B intersect in the empty set. In other words, they don't overlap. And that's definitely not the correct option because the Red Sox winning by 5 or more runs implies that they win. So it's certainly possible that both of these events occur. The second option says that A is a subset of B. In this option, every outcome that satisfies the condition defining A also satisfies the condition defining B. And that's indeed the case. If the Red Sox win by 5 or more runs, then they certainly win. So this is the right option. So in this problem, we want to show that if B is a subset of A, then the probability of B is less than or equal to the probability of A. This is a common sense property that we definitely want our probability measure to satisfy. If you know that one event implies another event, then that gives you some information about the direction of inequality between those 2 events' probabilities. The idea here is going to be to split A into B and then the part of A that doesn't include B. Since these 2 sets together make up A and they don't overlap by definition, their probabilities will sum to give the probability of A. This property of a probability measure is called additivity, and it follows directly from the definition of the probability measure as summing the probability masses associated with each outcome. Now we can replace this term with 0, and in doing so we know that we're not making the left-hand side any larger because this probability is greater than or equal to 0. So that means that the probability of A is indeed greater than or equal to the probability of B. In this exercise, we show that the probability of a union of 2 sets is less than or equal to the sum of the probabilities of those 2 sets. This is called the subadditivity property of a probability measure. The idea is to split the union of A and B into three separate pieces: the intersection of the two sets, the part that's in A but not B, and the part that's in B but not A. By additivity, the probabilities associated with those three sets have to add up to the probability of A union B. The probability of A minus B is equal to the probability of A minus the probability of the intersection. And similarly for the other set. And since this probability is negative, the right-hand side is indeed greater than or equal to the left-hand side. In the next problem, we'll start thinking about the expectation of a random variable. So just by way of review, a random variable is a numerical outcome of an experiment. So it associates with each outcome of the experiment a number. For example, if you're considering a lottery, an important random variable for that scenario is the amount of money that you win. So the probability space might consist of, well, for a lottery, it would be many outcomes. Let's say it's just these 6 outcomes. And your winnings for the 6 outcomes might be mostly zeros, but $1 million jackpot. And you can describe the situation by labeling each point, but the mathematical way of describing a labeling is a function. So we want to think of mapping these values to the real number line. And the probability distribution associated with this random variable is just the distribution of mass on the number line you get by pushing forward each of these masses to the number line. So maybe these 5 masses add up to almost 1. So there's going to be a probability mass here, almost 1. And maybe this one has a probability of 1 over a million. And so there will be a 1 over a million mass here at 1 million. This object with the probability masses here and here, this is called the distribution of x. And the expectation of x is just the balance point of the distribution. It's where we would have to put a 1-point support in order to get the number line to balance, assuming the number line itself is weightless and all of the mass is coming from these probability masses on the number line. And a formula for the expectation is to sum over all real numbers that real number value times the amount of probability mass sitting there for the distribution of x. So this is called the probability mass function of x, and it describes where the probability mass is on the number line. We can also do it over here on the probability space side, in which case we're summing over all the elements in the probability space, and we associate the value of the random variable at that element of the probability space with the mass associated with it, multiply and add. So in this problem, we're given a pair of random variables, x comma y, and we're told that they're uniformly distributed on the set 0, 1, 2, 3 squared. This means that if we look at these 16 points, each one has probability 1 over 16 of being the eventual value of capital X comma capital Y. And we're asked to find the expected value of x, the expected value of y, and the expected value of the sum. So in this scenario, x is equal to 0 if any of these 4 outcomes occur, and that has probability 1/4. Likewise, x is equal to 1 with probability of 1/4, as well as 2 and 3. So the expectation of x is 1.5. And in exactly the same way, the expectation of y is also 1.5, because it's equal to 0 with probability 1/4, 1 with probability 1/4, and so on. As for the sum, it's equal to 0 with probability 1/16, and it's equal to 1 with probability 2/16, because these two outcomes both have x plus y equaling 1. 2 with probability 3/16, 3 with probability 4/16, 4 with probability 3/16, 5 with probability 2/16, and 6 with probability 1/16. And if you work out this expression, it comes out to 3. And in fact, it's not a coincidence that 1.5 plus 1.5 equals 3. We'll see that in general, the expectation of x and the expectation of y always sum to give the expectation of the sum x plus y. In this problem, we eliminate the independence assumption on x and y. We have these two random variables that are defined in a way that's clearly pretty arbitrary. X is 3 if the random permutation we get by scrambling around 1, 2, 3, 4 at random starts with 1, 2, and it's going to be 2 otherwise. And then y has some other conditions. 6 if we see 2, 3 in the second and third positions. 4 if we see a 2 and then not a 3 in those two positions, and otherwise it's all 0. And we're asked to find the expected value of x, the expected value of y, and the expected value of x plus y. So we can represent the distribution of x and y in various ways. I want to do it by just writing out all the permutations and highlighting the various places where x and y take on different values. So x is 3 on those two permutations, and it's 2 everywhere else. I'm going to skip the arithmetic here, but these two numbers will indeed add up to give this third one. And in fact, if you think about it, you can split each of these factors into its x and y parts, distribute and rearrange terms, and you'll see that you can actually recover the sum of all these terms by suitably splitting up this sum here. And once you do that, you essentially have a proof that the expected value of x plus the expected value of y is the expected value of x plus y. So here's an extra question that isn't on the sheet. It was from the summer prep worksheet. So the question is, how many consecutive pairs of red cards does a well-shuffled deck have on average? So the idea of this problem is to illustrate how the linearity of expectation actually does have some surprising consequences. If you get used to linearity of expectation in the context of distributing the expectation symbol across a sum, then it feels quite natural because you're used to distributing things symbolically. However, in the context of this question, the results are going to be perhaps a bit surprising. So the idea is that the number of consecutive red pairs in the deck is going to be a sum of what's called indicator random variables. So we're going to put one random variable here watching the first two positions, and this random variable is going to be 1 if it sees 2 R's, and it's going to be 0 otherwise. And similarly, for the next two positions, we're going to have an indicator random variable. Call this first one x1, the second one x2, and it's the same idea. It watches those two positions. If they're both red cards, it gives a 1, and it gives a 0 otherwise, and so on until we get to the end. The very last one is going to be x51. There are 51 of these pairs. And clearly, the number of consecutive pairs of red cards is just going to be a sum of these 1s and 0s. So the desired value is the random variable x1 plus x2 and so on up to x51. And these are not independent random variables. If you know that x1 is 1, then that's telling you x2 is more likely to be 1 than if you didn't know that, because you know it's already got an r here in this position. And we're being asked to find the average value of this random variable. In other words, its expectation. And we learned that expectation distributes across addition. So we can write this as the sum of the expectation of x1 and so on up to the expectation of x51. And the thing is, these are now 51 separate problems. We are not doing the same single probability problem anymore. We have 51 separate problems, and we can solve them all separately. So we'll solve the first one, expectation of x1, by just considering that the probability that the first card is red is 1/2, since half the cards in the deck are red. Then the conditional probability of the second card being red, given that the first card is red, is 25 over 51, since there are 51 cards left in the deck and 25 of them are red, since that first one dealt was a red. The probability that x1 is 1 is equal to the expected value of x1. And also, the probability that x2 is 1 is the same as the probability that x1 is 1. Because if we're looking at the second and third positions, again, this is an isolated problem because we're simplifying the right-hand side here. And the second problem that arises is to find the expected value of x2. And when we're considering the expected value of x2, we can imagine dealing the cards in any order we want, and we can in particular imagine dealing the second and third cards first, in which case we're going to be in the same scenario as we were with x1, where the first card is red with probability 1/2, and the second card is red with probability 25 over 51. All of the x's have the same expectation, in fact, for the same reason. We're adding up 51 copies of 25 over 51 times 1/2, and that gives us a total of 25 over 2, which is 12.5. So we avoided having to think about the joint relationship between the x's here, which is quite complicated, because we were particularly interested in the expectation. If you just want to know expectation, then you can consider the expectations of each piece individually and sum them, and you don't have to think about the interplay between each of the x's. And you can run this simulation, shuffle a deck, and count the number of consecutive pairs of reds, and you're going to get very close to 12.5 if you run this experiment many times. So in this problem, we're thinking about conditional probability. And this is actually a very generic situation. You have some probabilities representing your beliefs about the world, and you make some new observations which need to alter those probabilities. So for example, in this scenario, you're 90% sure that your package arrived today, and you're 75% sure that if it had in fact arrived, then it would be on your doorstep rather than in your mailbox. When you come home, you don't see the package. And the question is, what's now the conditional probability that the package is in the mailbox, given the probabilities as you believe them, together with your observation that the package is in fact not on the doorstep? So we'll use the formula for conditional probability. The probability that the package was delivered, given that it is not visible, is equal to the probability that it was delivered and put in the mailbox. The probability is delivered and that it is not visible, divided by the probability that it's not visible. So we know that the probability that it was delivered and invisible is 90% times 25%. And the probability that the package is not visible is 10%, corresponding to it having not been delivered, plus that same value we computed in the numerator. And this works out to about 69.2%. So even though you were quite sure it was going to be delivered and you were pretty sure it was going to be on the doorstep, you're still rather sure that it's actually going to be in the mailbox, even after you don't see it on the doorstep. So this calculation that produces updated conditional probabilities based on evidence is called Bayes' rule or Bayes' theorem, and it plays a pivotal role in what's called Bayesian statistics, which we'll study later.